So, just like to welcome everyone, our new and some regular attendees to our webinar, Why Large Capital Projects Are Often Over Budget and What to Do About It. If you're attending for the first time, I'm the regular presenter. My name's Michael Trumper. I'm one of the principals here at Tabor Institute, and have been in the area of project and risk management and software development for over 20 years. Before we start, I'd just like to go over some housekeeping and basically how you can participate in the webinar. You see a panel at the top right corner of your screen, which will allow you to select your audio and also interact during the webinar. If you haven't done so, I recommend using the computer mic and speakers, as the audio quality tends to be better. Feel free to use the questions pane to ask questions during the webinar, which will be answered in the order they came in at the end of the webinar. If you're having technical issues, you can add those to the questions pane as well, or the chat, and we will try and address them as they come in. The webinar today is based on a paper that was written as a collaboration between Glenn Palmer, who is one of our consulting partners, and Lev Virine, who is the head of our development team and founder of Tabor Institute. The paper was based on an analysis of cost escalation in large infrastructure projects from publicly available data. The presentation will start with some case studies, then go on to the results of the analysis of the data, and one recommended process to manage these issues. Due to availability issues, I will be doing the presentation today. The average cost of large capital projects in North America and Western Europe continue to grow faster than inflation. This analysis of hundreds of large projects over the past 20 years and other data from multiple sources shows that if the trend continues, the cost of these types of projects will reach unsustainable levels. The reasons that we'll go over include resource issues, supply chain issues, understated estimates, and poor project planning. Political interference, ineffective bidding practices, and mismanagement can also play a significant role. This presentation will finish by proposing a process designed to mitigate some of these problems. This includes the integration of project risk management, risk analysis, and project controls. So the first case study, a widely studied example, is the extension of the Long Island Railroad from Queens into a new station across Grand Central Terminal on Manhattan's east side. The east side access cost estimates increased from $5.3 billion in 2002 to $11.2 billion in 2021. This makes it one of the most expensive per kilometer tunneling projects in history. Three main reasons were found for this cost overrun: is mismanagement, lack of oversight, and fraud. These are common root causes for cost overruns that occur in most large projects. Particularly problems included high payments to contractors and issues with the bidding process, politically connected unions, high profits of the design and construction companies, design mistakes and design changes, problems related to cooperation with other agencies, and a 15 to 25% contingency due to bureaucracy. Another example is the Monaghan train hall in New York, which was the merging of the Pennsylvania station with the city's former main post office building. This was a two-phase project, with the first phase starting in 2010 and the second phase ending in 2021. The total costs of construction were a staggering $1.6 billion when compared with the original estimate of $315 million. Another one is the cost of the California high-speed rail escalated from $68.4 billion in 2012 to $77 billion in 2018 in year of expenditure dollars, assuming a 2033 completion date. Here's an example from the UK, the HS2 high-speed railway, which will run from London to Birmingham and the East Midlands. The first phase is currently under construction and is due for completion between 2029 and 2033. Project cost in 2015 was estimated to be $56.6 billion, with current estimates going as high as pounds, as high as 115 billion pounds in constant dollars. The paper compared how costs differed between projects in different locales and economies. Though there can be many regional differences, the comparison is valid as construction of transit projects in cities are consistent in that they can use similar technologies. However, there has to be some adjustment for the length and depth of stations, as well as other parameters of the projects that can be significantly different. Here we see a comparison of the costs of two LRT projects, which have similarities in that they are in urban locations and use similar technologies. We can see that the labor rates are much higher, 15 times, but the costs are estimated 21 times more expensive for a similar project in Toronto as opposed to Addis Ababa. We will look at the factors that are driving cost escalation in North America and Europe. The data set used was from the Transit Cost Project that was collected by researchers at New York University. The data is very comprehensive and includes projects from around the globe. This data includes 850 projects that have been completed since the year 2000. These include rail, LRT, and subways. All cost data was from public sources. The cost data was normalized to account for local purchasing power at the midpoint of each project. And the costs were converted to US dollars and adjusted based on US inflation rates. And then finally, costs were calculated in cost per kilometer. So a fairly comprehensive database was available. The goal of the analysis included three objectives: to determine how construction costs worldwide are changing over time based on data from all projects included to the dataset, to determine if there are any correlation between construction labor wages in the country and the costs of projects, and finally, a qualitative assessment of the drivers affecting costs based on detailed analysis of the most expensive projects. This is a subset of 35 of the most expensive projects in the world with costs of over $600 million per kilometer. Due to the limitations of the data, a quantitative analysis of other factors affecting construction costs, which may be cost of materials, design features, and other factors, was not performed. So the first finding is that construction costs have grown faster than the rate of inflation. As of June 22nd, when the paper was published, new construction cost index forecasted a 14.1% year-over-year increase in construction costs by the year end 2022 due to labor and material costs continuing to grow. However, in retrospect, this spike, as we know, was driven by the COVID pandemic, which put massive strains on labor availability and supply chains. A classic black swan event that I doubt was on many companies' risk registers. So at the time of the analysis, the average US inflation in 2020 to 22 was 4.1, though it spiked up to 7.5% in 2022, but is now starting to moderate. In 2023 and 2024, the construction cost index appears to be stabilizing and is currently 2.2%, according to the Mortenson data, which is close to the historical average. This chart shows the gradual increase of cost per kilometer over the past 20 years that generally follows patterns of economic cycles, with a large spike in the 2022 and 23 years. These charts compare the construction worker wages and construction costs of transit projects per kilometer. In general, there's not a strong relationship between salaries of construction workers and the costs of projects. To make the relationship shown in the previous slide more clearer, this chart shows the correlation or lack thereof between salaries of construction workers and the cost of projects. In some countries, for example, New Zealand, Hong Kong, and Singapore, costs of projects are very high while wages are close to the mean. In other countries such as Norway, Switzerland, and Denmark, wages are high, but cost of projects per kilometer is below average. It indicates there are many other factors that contribute to the cost of transit projects. Some of these factors are related to design for the projects. For example, in some cities, stations are closer to each other, which require more labor to build. Some transit projects are built at grade, some elevated, and some in tunnels. The detailed analysis looked at the most expensive per kilometer projects, includes projects from around the globe. This includes some Singapore, San Francisco, Auckland, Hong Kong, New York, Munich, Montreal, Toronto, and Melbourne. At a high level, they all share some common features. All are in urban areas and all involve tunneling, which add to both the technical complexity and political and regulatory burdens. Main reasons behind cost growth: significant technical challenges. Most of the projects are in the city centers, and some of them are at a significant depth, with areas having complex geology. Issues related to planning, approval, and project management. So the technical problems are probably require significant labor construction hours to address. Otherwise, wages and project costs would be more closely correlated. The disconnect could be due to risk events that occurred during the construction. Project estimation errors, another source. The source of project estimation errors draws on the work of Flyberg and Kahneman, and can be categorized in two ways: deliberate. Danish researcher Brent Flyberg looked at large projects including roads, rail projects, bridges, and tunnels, and found that project planners consistently underestimate costs and overestimate benefits to secure project approval. Specifically, in 90% of large infrastructure project costs are intentionally underestimated. The average cost escalation was 27.6%. Rail projects experienced the largest cost escalation at 44.7%. Roads had a more modest cost escalation at 20.4%. Project planners intentionally downplayed the probability of risk affecting the project. In one well-documented case, Eurotunnel, the private company that owns the Channel Tunnel between France and the UK, initially assured investors that the cost escalations would be limited to 10%. However, the actual cost turned out to be twice as high due to underestimated risks. I think that's actually quite a kind take on what actually happened there, but that's my opinion. Unintentional. At the same time, there is another driving force behind project estimation errors. It is the optimism bias, or planning fallacy, as described by Daniel Kahneman. This is the tendency of project planners to be overly optimistic about the outcome of planned actions, and therefore overestimate the probability of projects being on time and budget. Particularly, project managers often fail to account for risks or other factors that they believe are outside the specific scope of a project. What this chart illustrates is the influence of these factors based on the magnitude of projects. Smaller projects with less complexity are subject more to optimism bias. Large projects, by their very nature, are very complex and often difficult to understand, which lends itself to deliberate misrepresentation of possible costs. This is a debate that's not settled, and I would hazard a guess that both can significantly impact project costs. So what are the reasons for other cost overruns that were identified? Highly inflated change orders, poor planning, poor inexperienced project management and engineering, aging construction workforce, poor claims management, and a lack of true risk management process. We'll look at these in detail in the next few slides. Inflated change orders. They can be highly inflated and often favors the contractors. I believe this is probably due to the sunk cost fallacy, where ownership groups do not want to, are unable to, or are affected by the sunk cost fallacy, where they can't. Once they have a large capital expenditure that they put into something, they are not going to walk away from it, and that gets leveraged by the contractors. In addition, because of the change orders, you have to bring in additional contractors may be required to complete the work on time. Poor project planning. High-level summary schedules lack the detail, which might reveal execution risks. This may cause a false sense of security and assumptions that the completion date is possible. The remedy here is fairly clear, as it provides insight into whether this project is worth the financial and reputational risks that would come with winning the project. This finding can be summarized by the Peter Principle, in which people in a hierarchy tend to rise to a level of respective incompetence. This is not meant to be a slur on anyone. It's just that employees tend to be promoted based on their success. So success moves you up the food chain in previous jobs until you reach a point where you're no longer competent. It's outside your skill set. You're asked to do things that you don't have any experience in. In construction, this can be summed up as most engineers make poor project managers. So all project managers need to have spent time in the field. Many lead engineers become project managers when their project managers leave the company, and this approach seldom works. Engineer's real client is the project's construction manager, and this has to be emphasized in all projects. So the engineers are working for the project's construction manager and probably should not be moved into a project management position unless they've shown some flair for that. Aging workforce. So less aging workforce, less labor available can be driving up costs. In my own experience and observations, though, this trend appears to be reversing as lately we have more emphasis on developing a skilled trades workforce. So a personal anecdote that I have a friend who has a senior position in a government ministry for advanced education. He has advanced degrees. His father was a university professor. His mother had a postgraduate degree. Excuse me, got a little bit of a phlegm going on here. So his family with a tradition of higher learning. At the ministry, he was tasked with developing a plan to address the educational requirements for the future labor force. This includes all areas of the economy. And the major finding of the report was that they had to refocus on developing skilled trades. Not surprising in itself, but my highly educated friend from a family of scholars pulled his two sons aside and told them he would not be financing any university degrees. He would support them in getting a trade, as this would guarantee them a well-paying job for life. He added that if in the future they wanted to pursue a university degree, the university would always be there, ready to take their money. So perhaps with this change in attitudes and about the value of, I'm going to say, manual hands-on labor, we might be seeing a turnaround in these attitudes, and this might be resolved. We might see some resolution in this in the future. Poor claims management. They get expensive due to slow responses, incorrect methodologies used to analyze the claims, and probably the biggest one is waiting for the project to complete so they can actually analyze the delays. Finally, so the favorite saying of mine comes from Tim Lister, a software engineer and a widely cited author. He's risk management is how adults manage projects. I have to admit that coming into this, when I first came in, I was a bit naive and often surprised at how undeveloped the risk management processes are in some organizations. Instead of being seen as central to project success, its approach is just another bureaucratic requirement of little value in actually getting on with the actual work required. Here's a list of the standard shortcomings that were identified. Creating a risk register and then letting it sit there and not updating it. Not using high quality analogous data to build your estimates. Not using experienced brainstorming moderators. Not revisiting the risk assessment on a regular basis. Not using structured processes, and not incorporating the analysis into the project schedule. So that's an integration of the practice of risk management and schedule, project risk analysis or schedule analysis. In this last section, we'll cover a proposed solution. Given that Tabor Institute is in the business of developing project risk management software, it shouldn't be a surprise to you that this is one of our recommendations. So first is use a structured process. Previously, we've written a few books on quantitative methods and how psychology of project decision making, and we always refer to this as the 3 C's: consistent, continuous, and comprehensive. Basically, when we say a structured process, it means process must be applied consistently. Same processes with some tailoring to account for project size and importance has to be applied to all projects. Processes have to be continuous on a well-defined schedule. Where this falls down is the example of the stale risk register that hasn't been updated. And that comprehensive means you need to ensure that you're looking at all possible sources of risk. Use an experienced, disinterested third-party experts who run brainstorming sessions. It's important that your experts or the person who's moderating or running these sessions isn't part of the project team. Identify and assess every high impact, high probability risk and manage as required. I found this, reading the paper, I found this recommendation interesting. Assign an experienced construction person to manage each high cost, high probability risk. Have them produce a peer-reviewed action plan that includes a time required to implement the plan. And here's the one, it should be a different manager for each of these high or critical risks if the risks are concurrent. So that could be a challenge, HR challenge. Assign schedule milestones in the schedule. There should be a decision to implement milestone on the date that reflects the latest possible date to implement. There should be a review risk milestone 30 days prior to the decision to implement to make sure the risk has not changed. An interesting note on this finding or recommendation is one of the most successful mega projects was the expansion of the Heathrow Airport. I've heard it described as a wicked problem and that there were no single solutions that would satisfy the demands of all the stakeholders. One of the key principles that they used that underlay the success of the project was that the project team adopted was to delay decisions until the last possible moment. This allowed, and I think this is reflected in this decision to implement, the latest possible date to implement. This allows this principle allowed this project team to make the last minute changes as facts on the grounds changed. So it gave them the flexibility, because once you have facts once something's built, that decision is made. So by delaying it as much as possible until they made those decisions, they were able to give themselves the flexibility to meet new requirements and demands. The idea behind this is, along with project controls that are reflected in the as you can see in the actuals, continuously regular scheduled risk analysis on the results that account for project actuals or actual project progress is critical. Along with having processes in place that allow production rates to be quickly analyzed via project controls and risk analysis, along with this, having processes in place that allow these actuals to be communicated and shared is key. Old, stale data often means that the time to make an effective decision has passed. This chart or illustration shows a process of continuous mitigation and response planning. We're looking at a burn down where we're looking at the results of this is sort of almost a classic we call it critical event chain visualization, where we can see where risk can occur. Then we put in response plans if we have them in place, and we can see how it would change. Instead of chance of meeting a deadline gets reduced because of risk events, but if we have effective management processes and responses, then we put them in place and the project can recover. Monitoring the chance of project completion on budget with risks and uncertainties. So you need to estimate the cost at all stages of the project. And forecasting project costs with actuals. So we brought that up earlier. This is a simple chart, and we're seeing the original budgeted estimate on the red line We can see the actuals as the green line, and then we can see the forecast going out. And that, we want to call it cone of risk and uncertainty, is generated by the risk events and uncertainties that we have around project costs and schedule. So conclusions. Analysis shows that the average cost escalation for construction project is around 5% per year, which is higher than inflation. In addition to planned cost escalation, there's this significant cost overruns for many projects. There's little correlation between construction cost per kilometer and construction wages in the country. Construction projects are often over budget because of errors in project planning. Integrated project risk management, risk analysis should be, and project controls can be effective. Two charts can be useful to monitor project execution with risk and uncertainties, chance of project completion, and project cost over time. So I want to finish off with some final thoughts on this as I went through this. 10 years ago, I co-authored a book called Project Think that focused on the psychology of human decision making and how it affects projects. At the time, my preferred title was Project Delusions, as I thought it more accurately reflected what we covered in the book. And though this data does show there are numerous sources that drive cost escalation, I still believe that the root cause of almost all project failures, as my colleague of mine calls it, is an HR problem. A problem rooted in our cognitive and psychological constraints. So with that, I'd like to thank everyone who attended. And if you do have any questions, please feel free. Oh, if you have any questions, I'm just looking over them right now. Is Risky Project Professional file available for students if possible? I would like to review how the risk assessment and schedules were done. Yes. If you contact us at sales or support at entabler.com, we'd be happy to help you out with that. So I don't see any other questions. Thank you again. Thank you for taking time out to attend our webinar. And as mentioned, if you have any questions in the past, feel free to reach out and be happy to discuss with you. Thank you.